Hey, what's up, Chem peeps? Let's take a quick look at some titration questions that you're going to have to work with this unit. As you take a look at your questions, a lot of them come back to the same titration curve. There's a lot of information and a lot of things that you need to understand when you look at a titration curve. And so as you look at the one that you're provided with in your notes, right, we've got a weak acid of unknown molarity, and we're titrating it with sodium hydroxide, a strong base. Now, before I dive into all the questions that you have to answer, I want to take a couple of minutes and just talk about what a titration looks like at the particle level, right? So, in a weak acid, strong base titration, imagine everything I have here in blue is kind of what's in my flask initially, right? My analyte in this case is the weak acid. Notice I recognize visually that it's weak because there are, just HA molecules and they're not ionized. Now, I'm giving you a little preview here. There's 4 HA molecules, right? We have an unknown concentration. So when you think about, actually doing a titration, you're really working blind, right? So when you do the titration, you're really taking your sodium hydroxide, in this case, adding it to your flask, and you're either looking to see a large change in pH because you're monitoring it with a pH probe, or as you add it, you're also thinking about maybe having an appropriate indicator so that when you have hit that equivalence point, you get this brilliant color change, ding, to let you know that you've reached the equivalent point, that you've reached all of the acid, right? And as you think about this reaction and most of the acid base reaction that you're going to do, in general, it's acid plus base forms water and a salt. And many times you'll also see the net ionic equation. Remember that in a net ionic equation, we remove the spectators. And because this is a weak acid, it's going to stay together. The strong base will be separated, and you'll form water and your aqueous salt, which is really individual sodium ions, and A minus ions, which are the conjugate base of your weak acid. And this really just focuses on the things that are going to affect the pH in the solution, right? And so it eliminates the spectators, like in this case, just the sodium ion. So I've got here on my screen right now the what's called the molecular equation, which you're probably used to writing, and the net ionic equation. But either way you look at it, the goal is to recognize that the ratio between the acid and the base is 1 to 1, right? And so as I think about what I had here in my flask, right, I am going to give you a view that you don't normally get to see when you're doing a titration, right? You know that there are 4 HA molecules in here. So as I think about my reaction, right, it's a 1 to 1 ratio between my acid and my base. So if I have 4 HA molecules, I need 4 NaOHs to completely use them up in order to reach my equivalence point. But that's something that you don't normally get to see, or you're not privy to, right, before you do the titration. And so what you're doing is you're adding, in this case, the strong base to your weak acid solution. Now, I'm going to focus on just the added hydroxide. The sodium is a spectator. It's kind of floating around in solution, right? But as I add the hydroxide, right, the HA is there to do this, right? We're going to neutralize it and form water and, yes, a salt. But again, if we're just focused on the important things, conjugate base, which is, part of that salt. And so watch it happen. Oh my gosh, right? The H plus from the acid, the OH minus that was added form water, and I form conjugate base. As I keep going, right, I'm going to add more sodium hydroxide. Again, recognizing sodium here as a spectator. My acid swoops in, neutralizes it, forms water and conjugate base. As you think about this point in the titration, again, when I do the titration, I don't know that I've hit this point, but I have reached what's called the half equivalence point. And we'll come back and talk about that in a minute. But just recognize here, my weak acid concentration and conjugate base concentrations are the same, right? I've used up enough of my HA that it's decreased by a certain amount, and I've made A minus its conjugate, so that at this point the concentrations are equal. As I keep going, though, right, I use up more and more of my weak acid and form more and more conjugate base until I have added a stoichiometric amount of strong base as weak acid that I had in there originally, right? So remember, I originally had 4 HA molecules. I added 4 NaOHs, and now, right, I have reached what's called the equivalence point. Any more strong base that I add, notice there's no longer any acid there to neutralize it. And so we're going to have a huge jump in pH. And so whether you're monitoring this with an indicator, you would have seen a color change, hopefully, by this point, if you picked the right indicator. Or if you're monitoring with a pH meter or a pH probe, you would see a huge jump in pH because we've got a bunch of free-floating hydroxide now. So that's just kind of a preview to this set of questions. As you think about kind of what's going on here, I'm also going to ask you to kind of think about the ratio of weak acid to conjugate base as you move throughout the titration curve, right? So as you think about kind of where we're at here at point Q, it's, at this point, we have virtually all weak acid, no conjugate base, right? Remember, we're in a situation where we haven't even done the titration yet. We've got our flask of weak acid. We haven't mixed any reactants together yet. So here's kind of our starting point where it's all weak acid, no conjugate base yet, right? And then as I continue the titration here at point R, right, I'm using up some of the HA. So it's decreasing the concentration of the weak acid, and I'm starting to make a substantial amount of A minus or its conjugate base, right? At this point, anytime you have weak acid and its conjugate base, you have a buffer. Now, it's not an ideal buffer, but it is a buffer because I have weak acid and I've started to form conjugate base. As I keep going here, this is that special point that I was talking about, point S, right? Where at this point, the half equivalence point, and I don't realize it's the half equivalence point yet, right? But at this point, I have consumed enough of my weak acid and produced enough of my conjugate base that those two things are now in equal concentration. So not only do I have a buffer, right, but now I have an ideal buffer because I've added half the amount of strong base, NaOH, as original HA molecules I had, right? Remember, I had 4 HAs originally. I added 2 NaOHs. I've used up 2 of the weak acid, and I formed 2 conjugate base. So this is not only a buffer, but it's an ideal buffer, and that occurs at the half equivalence point. Again, there's no way to know that at this point in the titration. As you keep going, right, you are going to continue to use up your weak acid and continue to make more conjugate base. Still a buffer, right? But it's still going to be a little more basic than we see with an ideal buffer because there's more conjugate base than there is weak acid. And then we finally reach the moment we've all been waiting for, right? Here is where we reach what's called the equivalence point. At the equivalence point, we have used up a stoichiometric amount of weak acid as strong base that we've added, right? And here is, essentially we're now down here, right? So I've completely turned all of my acid into its conjugate base. And this is a really difficult point to hit, right, when you're doing the titration. But we've essentially, gotten to this point where we have, reacted everything in a perfect amount according to the balanced chemical equation. And again, it's here that you should start to see a bit of a very slight color change if you've chosen the right indicator. And if you are using a pH meter, you're going to start to see a really large jump in pH. And so as you think about these questions, right, I encourage you to think about what's going on at the particle level, what's going on in terms of the concentrations of the weak acid in this case and its conjugate base, A minus. But that's just kind of to preview this for you. I know you're here for the answers only, but it's kind of to help you understand what's going on or what's going to happen in just a bit here. So let's get to the good stuff. Let's answer some of these questions. The first question is asking you to think about at what volume the number of moles of NaOH added equals the number of moles of HA in the sample. So here, as you think about this, again, just remember that we had originally 4 HA molecules, right? And so when we've here we go. So here's my starting point, right? We're looking for like when I've added 4, in this case, NaOHs because it's a 1-to-1 ratio, right? That at that point, right, I have reached what's called the equivalence point. So it's at 40 mils that we have reached the equivalence point. And again, you're going to recognize that because you're going to see it on a titration curve because you're going to see a huge jump in pH. And if you're actually doing it in the lab, you're going to see it visually if you've picked the right indicator by having a visible color change. The half equivalence point is important, but that's not where we've added a stoichiometric amount of, in this case, strong base as original weak acid. Question number 2 says, based on the data, which of the following is the appropriate molar concentration of the unknown acid? Yeah, good question, right? This is a really difficult question. We are going to use this equation, molarity of acid times volume of acid is equal to molarity of base times volume of base. And we can do this because we know that the ratio between our weak acid and the strong base is a 1-to-1 ratio. And so essentially what we're doing here is whatever the molarity of the acid is, moles over, I'm going to do volume, right? If I solve this for moles, right, moles of acid is molarity times volume. And the molarity of the base is also moles over volume. And I again solve it for moles, right? It's at the equivalence point because this is a 1-to-1 ratio where this number of moles of acid is equal to this number of moles of base. And so because moles is equal to moles, we can set these two quantities equal to one another. And so as you think about answering this question, right, the molarity of the acid is what we're looking for, right? We don't know the concentration of this acid. We know that we initially started with a 50 mil sample. I don't have to convert to liters here as long as I make sure the volume on the base is also in milliliters. We know the concentration of the base is 0.1 molar. And here's probably the hardest part, like what volume do I use, right? We're, again, thinking about at what point are these two number of moles equal. That's at the equivalence point. That, in this case, is at 40 milliliters. So I'm going to drop in 40 here. And then we have to do some math, which, is definitely tricky without a calculator. 50 times x is, just x times 50. And over here, this is going to be 4, right? 40 times 0.1, or what's a tenth of 40. And then I have to divide each side by 50. Oof, right? So I'm in a situation that is really difficult for me, right? 4 divided by 50. Some of you may not have may not struggle with this, and you can, clearly tell like what the correct answer is. But if you are like me, it may be helpful, maybe not, to use scientific notation, right? 4 times 10 to the 0 over 5 times 10 to the 1. Again, maybe not super helpful, but think about maybe moving your decimal point, right? 40 times 10 to the minus 1, which is just this in a different notation, over 5 times 10 to the 1, right? 40 divided by 5 is 8. And then -1 -1. We're going to have 10 to the -2 as our molar concentration of this acid, right? The molarity of the acid, 8 times 10 to the -2, or 0.08 molar. Again, you might be way better at math and just be like, oh, I know how to do this, right? But there we go, number 2. Number 3, right? A student carries out the same titration but uses an indicator instead of a pH meter. If the indicator changes color slightly past the equivalence point, what will the student obtain for the calculated concentration of the acid? Oof, yikes, right? You're actually going to do the same calculation. You don't necessarily have to do this if you understand kind of the math involved, but I like to write this out as just kind of a visual, right? We're solving for the concentration still of our acid. Our volume of the acid, the 50 mil original sample, isn't going to change. The molarity of the base isn't going to change. That's not what's going to cause the error. It's going to be here, right? If we are going past the equivalence point, the equivalence point is 40 mils. If it changes past, we're going to keep adding base until we get the color change. So we're going to actually add a little bit more. And so I'm just going to say, usually when you go past, it's like a little bit past, like 40.2, right? Or 41. But I'm going to say for the purpose of this, let's just say we totally lost it. And I put in 50 mils of base. Again, it's x times 50 is equal to now 5, right? So when you solve for x, it's 5 over 50, right? So even if you couldn't quite figure this out, recognize that 5 over 50 is going to be a calculated concentration that is larger than 4 over 50. So remember, you're going to see a lot of questions that ask you to kind of think about error analysis. And many times it just comes back to you thinking about what steps did I take? What math did I solve? And how does the error affect the numbers in that math or in those steps? So, just be thinking about that for those first 3 questions. And then we get to hopefully something that you can now answer very quickly thanks to my thrilling example using the particle diagrams that you saw here, right? So this next series of questions is asking you about what is in largest concentration at these different points along the curve, right? So I'm not going to reiterate it, but I encourage you to go back to the beginning of this video if you need help kind of understanding what is in largest concentration at each of the individual points, right? But just kidding, I am going to go back and do it, right? So here I am at my initial starting point, my point Q, right? Just acid, not part of the question, but just acid to start, right? As I keep going, right, as I get up to part R, I have added some hydroxide and formed some conjugate base. But still, at this point, more acid than conjugate base. So for this one, pretty straightforward. We've got mostly HA in solution. We haven't even reached the half equivalence point yet. And then we got to keep going, right? As you think about the different points along this curve, right? Next one is S, right? And that's a really important point, right? We've added enough strong base to use up half of the weak acid. And it's at that point, right, that we have generated enough conjugate base that it now matches the amount of HA in solution. And so here we actually have equal concentrations of the HA, the weak acid, and its conjugate base. But this one, the next question is asking us about, what's going on, not at point S, but at point T, right? So at point T, we still have a buffer, right? We've added some hydroxide here. We've used up more of the weak acid, and we form more conjugate base, right? So in solution, right, the most, the thing that's in greatest concentration right now is the A minus, is the conjugate base. So as I think about these questions, right, definitely some tricky stuff here. And then I get to point U, right? As you think about the titration, when I get to point U, I'm way up here, right? So I've added, at this point, I've gone past the equivalence point. I've got like 50 mils of 0.1 molar sodium hydroxide. So I don't have enough hydroxides here, right, in my little particle representation, right? I've used up all, so here's my equivalence point, but U is like not only at the equivalence point, but way past it. So like, here's the next one. I'm gonna have to add like a bunch more hydroxide. So it's just like loads and loads of hydroxide at that point. And so we've got lots of hydroxide here, and that's gonna be our answer to this next question. And then it says, at what volume of added NaOH in the titration is the HA A- buffer most ideal? That's the half equivalence point. And again, you can't identify that unless you've completed the titration, or like in this question, you're given a titration curve that's already been done for you, right? You're looking for where's the equivalence point, where's that big jump in pH, or big drop if you're doing the opposite, right? And then go to half that volume. That's the half equivalence point. That's where the concentrations of those two things are equal. Then we get to our question number 8, which is a really important question, a really common question. Which of the following most closely approximates the Ka of this weak acid? And so when you think about this question, I know it's tempting to think, okay, gosh, Mr. Boylan, throwback, I can do this, right? I know that the Kas, when we talk about putting acid in water, and forms hydronium and conjugate base. And I know that I define Ka as any K, right? Products over reactants. Don't do this for this question. Over reactants, right? I know what the initial pH is, right? Or I can kind of guess, right? And I know that pH is directly related to hydronium ion concentration. So what I could do here, right, is I could, set this ice table up. My pH is around 2, right? So what that means is I've got a hydronium ion concentration that's around 1 times 10 to the minus 2, which means this went up. This also went up. Don't do this, by the way. This is what a lot of students try to do, right? They try to think about, how have I solved for Ka in the past? We've solved for the concentration from the earlier question, right? And we could solve this. Oh, that's actually a fairly big change compared to 0.08. That's actually going to be 0.07. But, we try to think about ways we've already solved for Ka. And technically, I suppose you could do this or something like this, but the point of this question isn't any of that, right? The point of this question is to recognize some important things about your titration curve. And here it's about recognizing that when you do have your Ka expression, right? This is how we define Ka, products over reactants, when we put the acid in water. You can rearrange this equation, right, and solve it for hydronium. So algebraically, I could multiply each side by HA and then divide by A minus. So acid over base times Ka, right, I just brought these two things over to the other side, equals hydronium ion concentration, right? We use this when we're working with a buffer, which is what we do have once we start dropping in that base. And it's important to recognize that there is a point where these, on your titration, where these two concentrations are the same, and therefore will drop from the calculation. And so you can very easily determine the Ka by looking at your titration curve at the half equivalence point, because it's there that this is true, right? So as I think about my titration curve at the half equivalence point, which is at 20 mils, right, I have a pH of about 4, right, a little bit less than that. So that means my hydronium ion concentration is going to be about 1 times 10 to the minus 4, right? So remember, it's here that Ka is equal to hydronium ion concentration. I'm looking at pH of about 4, right? And recognize that we have this formula, negative log of hydronium ion concentration. So if pH is about 4, just to estimate since we don't have a calculator, and I'm trying to solve for hydronium ion concentration, right, it's going to be 10 to the negative pH to give you the hydronium ion concentration. So Ka, again, we're approximating here, it's going to be about 1 times 10 to the minus 4. Whew, right? Really important thing here about the half equivalence point. Also important to keep in mind, sometimes you'll be asked, think about the pKa, right? pKa, if I take the negative log of each side of this equation right here, it becomes pKa equals pH, right? So sometimes, just be aware, you would have to recognize that pKa is 4 because the pH is 4 at the half equivalence point. So just some things to be thinking about as you interpret your titration curve. That's a lot right there, right? Those 8 questions as they relate just to a single titration. So expect a lot of work coming from just a single titration curve. Next, question number 9. Right? This question is a doozy. There's a lot to it here. There's a lot that you won't actually see on a multiple choice, but that would be great practice for a free response. As you look at this question, it says a student titrates a 20 mil sample of 0.1 molar methylamine using 0.2 molar HBr. The Kb for methylamine is 1 times 10 to the minus 5. So we've got a classic weak base strong acid titration. And I'm going to jump down here at the very bottom to give myself a little more room for this. When I'm writing a net ionic equation, right, I've got my weak base, the methylamine, and I'm adding strong acid, HBr. Now, this one for me is the most challenging acid-base neutralization reaction to write because I'm typically looking for the formation of water and a salt. But, right, I'm not really going to get that here, right? As I think about what's happening, my acid is giving up the hydrogen ion to my base is accepting it. So once my methylamine, right, accepts the hydrogen ion, it actually becomes this CH3NH3 plus acid, conjugate acid form, and the HBr has, been left behind just as the bromide ion. And so, this doesn't really look like a classic equation for an acid-base neutralization because I'm thinking, where's the water, right? So a couple of things, right? We need to write a net ionic equation. And when I write a net ionic equation, I have to get rid of the spectators. And there's a couple of ways that you can do that, right? If you treat the HBr as a strong acid, recognize that it's going to separate into its individual ions. Now, you can write it as hydrogen ion and bromide ion, or you can write it as hydronium ion, because remember, this is all happening in water, and bromide ion, right? So as I think about my products over here, right, I'm going to get that CH3 NH3 plus conjugate acid of my methylamine and my bromide ion. The net ionic is going to have, this equation without the bromide. That's my spectator. It appears in the same form on either side, right? So I would, want to drop this to give you my, my net ionic equation. I actually like this way down here, right? If you treat the hydrogen ion as hydronium ion in solution because everything's in water, because you do actually get to see the formation of the salt and the water, right? Now, if you think about, what's happening here, it's still the hydrogen ion going to the methylamine, right? But if you write it as hydronium, what's left behind? Oh, water, right? So I've got the formation of my salt, which is kind of a complex looking salt, and water. So, a little tricky here as you think about writing the net ionic equation. Again, I would need to get rid of the bromide if I were to use this one as my net ionic equation. But I kind of like it there just so you can see how it is, acid plus base forms salt and water. And the net ionic equation is really just focusing on the stuff that's important for the chemistry right now. So the first part of this is writing the net ionic. Both of these are acceptable, right? So this is a net ionic equation, and this is a net ionic equation for a weak base, strong acid titration. And you want to be comfortable with this because it looks a little funny, especially when you're just, practicing for the first time. But that's my net ionic equation. The important thing is the ratio here between my base and my acid is 1:1. So as I think about this question, I'm then asked to sketch, and this is key, a titration curve that results when a total of 40 mils of the 0.2 molar HBr is added dropwise to the 20 mil volume of 0.1 molar methylamine. Whew, dang, right? So as you think about this question, when you're sketching, you don't have to really do a whole lot of math. If you're comfortable with the math, you absolutely can. But when you're pressed for time, here are the pro tips. One, come up with an initial pH, right? We're starting with methylamine, which is a weak base. So I'm just going to make sure that my initial pH falls in the basic range, right? Greater than 7. It's a great start. I'm adding strong acid, HBr. So after I've added the 40 mils, right, I'm going to be very, very acidic. The only real math I have to do is figure out, at what point as I'm dropping in that strong acid, is there going to be a huge drop in the pH, right? When do I hit the equivalence point? And so here I'm going to use the molarity of acid times volume of acid equals molarity of base times volume of base. Now, in this case, we know the molarity of the weak base, the methylamine, is 0.1. And the volume of the base that we have in our sample is 20 mils. We know the concentration of our acid. It is 0.2. And we're looking for the volume of acid that I have to add to reach the equivalence point or the stoichiometric point, right? So this one's, pretty easy for me, and I'm bad at math, but this is going to be 2. Wow, I said it was easy, and here I am on the struggle bus. Divided by 0.2, divided by 0.2. So the volume of the acid is going to be 10 mils, right? So this is where my equivalence point is going to happen. Here's where I'm seeing the big drop. And so as I think about this question, right, I've got to recognize that, this is a weak base, a strong acid. So at the equivalence point, the pH is not going to be 7. It's going to actually happen in the acidic range. Again, I don't know where this is going to happen. I don't know any of these points, right? Other than I know it's going to start basic, end very acidic, and when I do hit the equivalence point, it's going to be more acidic, and it's not going to be neutral. And then I'm just going to sketch my curve, right? Again, think about the lab we've done in class. When you make a curve, right? Don't do this, right? Don't break Mr. Boylan, right? Don't do this or something. Like, that's not what a titration curve looks like. You are going to, initially see a bit of a decrease in pH, right? But then you've created a buffer, so it's going to kind of plateau off a bit, right? It's going to, stay fairly constant. And it's not until you come close to that equivalence point that we see the big drop, right? In the pH. And then it's going to, kind of plateau back off again as we have just a strong acid in your solution, right? So I've made a quick sketch here. Again, I haven't really done any math except determining the volume at which we've hit the equivalence point. And that's what we're really looking for in a sketch. If you look at some of the practice videos that I put together, I do show you how to figure out some of the math along the way. But if you don't have time for that, which, many times we don't, just come up with a sketch of the curve that, kind of you think best represents based on what you have in the time you have available, right? If you have time, right, you absolutely, I set this up so it's kind of nice for you to work with, right? The KB of the base is 1 times 10 to the minus 5. So I have to remember, right, that KB times now base concentration over acid concentration is equal to hydroxide ion concentration, right? So at the half equivalence point, which is going to be halfway, right, at 5 mils, these two things, the base over the acid, are going to drop from my calculation. So it's just Kb equals hydroxide at that point, right? And, as I think about my Kb, which is 1 times 10 to the minus 5, 1 times 10 to the minus 5, if that's my hydroxide and I take the negative log of that, that means my pOH at the half equivalence point is 5, or the pH is 9. So there are some things that I can do, right, to kind of like make this sketch a little, truer to what it's going to be, right? I know that I have a 0.1 molar weak base, and it is a 20 mil sample. So I know the concentration. So I can, kind of figure out I can do one of those like KB equals X squared over initial concentrations kind of thing if I want to, right? Because I know KB, so 1 times 10 to the minus 5 equals X squared over 1 times 10 to the minus 1, right? And then multiply these and get 1 times 10 to the minus 6 equals X squared, square root that. My hydroxide ion concentration initially, right, is going to be 1 times 10 to the minus 3 molar, or pOH of 3. Oh, what do you know? Just so happens that I nailed that initially, but that's because I'm just a genius. No, I actually did this problem before. Long time ago. Okay. But now to the actual multiple choice question. At 5 mils, how does the concentration of the weak base compare to the acid? So remember, this is flipped, right? We're starting with all base. As we add the strong acid, we're making the conjugate. But once you get to the half equivalence point, oh my gosh, these two things are the same, right? So here until here, right, it's mostly the methylamine. We're starting to form some of its conjugate acid. At the half equivalence point, they are the same, right? And then once you get past that half equivalence point, there's going to be more of the acid form, the conjugate acid, than the weak base. Whew, dang. I know. As you look at the last one, this is the last one. I know. You're like, get me out of this class. It's fair. It's fine. If you look at this last one, right, question 10, it's very similar, but it's asking you about now weak acid with strong base. And so I've got this HNO2. I'm adding it to my strong base KOH, and I'm going to form water and a salt. So this one's a little nicer, follows the rules, I think, a little better. But this is not a net ionic equation. This is like the molecular total ionic. Weak acid stays together. Strong base is going to be completely ionized. I'm forming water, and I've got this very soluble salt. That potassium ion tells me so. So it's really potassium ions and nitrite ions floating around. So I've got potassium ion as a spectator. So the net ionic equation is my weak acid plus hydroxide forms water and conjugate base, right? The conjugate base is part of the salt that forms. We very often say HA plus OH forms H2O and A minus conjugate base. Just, we're using NO2 instead of A. But that's our net ionic equation. Again, it's a 1-to-1 ratio between our acid and our base. And from there, it's the exact same thing, but flipped, right? So in this case, we've got 50 mil sample of 0.5 molar nitrous acid. So I'm going to be acidic, right? I'm just going to jump way down here to the acidic range to start. And now we're adding base. So by the time I finish adding all the base, we're going to be, very, very basic. And then again, I have to think about, all right, I know that it's weak acid, strong base. So whenever I figure out what the equivalence point is, it's going to be in the basic range, right? And again, I encourage you to use this: molarity of acid times volume of acid equals molarity of base times volume of base. This time, we know the molarity of the acid is 0.5. We know the volume of the acid is 50, right? And the molarity of the base that we're using is 1 molar. So what is the volume of the base added, when those moles of acid and base when those moles of the weak acid and added strong base are the same, right? Where's the equivalence point volume? And in this case, 0.5 times 50, a little easier, divided by 1. 25 mils is our volume of the base at the equivalence point. So at 25 mils, it's going to be a basic, pH. And then I have to sketch, right? So I'm going to sketch a roux here. Again, I'm going to recognize, all right, I'm going to see, an increase in pH, but then I got this buffer region, it's going to increase a little bit. And then it's like, boom, here we go. I've hit my equivalence point, and it's going to plateau out, Again, just a rough sketch of your titration curve, recognizing again, I do not want to see, please do not break my heart. Please do not break my heart. Don't do something like this. It just, that hurts me a lot. So here we go. Here's my curve and the actual question. Again, 5 mils, right? Now, at this point, this is the half equivalence point. We are well before the half equivalence point. So we're going to have more of the weak acid than we do conjugate base. Ooh, dang. That's a lot, right? Wow. But hopefully you can skip around, put things in double speed, and I hope you find that helpful. All right, you'll have a great weekend. Stay warm.